With Nagaro's diverse range of resilience engineering services, you can build robust and reliable systems and ensure business continuity. Our tailored solutions ensure that your brand has the unbeatable advantage of staying at the top, even during unforeseen events.
All right, so hi everyone, I'm Sarthak Jain, a senior software developer at Harness and also maintainer at LitmusChaos project. Thank you for attending Chaos Carnival and special thanks to our sponsors for supporting our community and this event. So we have yet another interesting session for you, and for this we have with us Akash Srivastava and Neelanjan Manna, who are maintainer at LitmusChaos, and we'll be talking about chaos engineering, enhancing application resiliency and security the right way. So this is going to be a recorded session, but yeah, the speakers will be with us to take any questions at the end if you have any.
Hey folks, welcome to the Chaos Carnival. My name is Neelanjan and I would like to welcome you to this session where we'll understand how chaos engineering can aid at assessing your application's resiliency and help you bolster its security. Also, we'll take a look at how LitmusChaos can simplify your chaos engineering requirements with its extensive suite of chaos experiments. Before we get into the talk, I would like to briefly introduce myself. I'm a software engineer at Harness and have been previously working at Chaos-native. I'm also a maintainer of the CNCF LitmusChaos project, a cloud-native framework for performing scalable chaos engineering. In my day-to-day work, I'm responsible for assessing the resiliency requirements for any given scenario and authoring chaos experiments that can suitably validate the resiliency of an application for different scenarios. So today, we'll be discussing a few of these scenarios which make up for a compelling outlook on an application's resiliency and security needs.
Hi everyone, I am Akash Srivastava and I am a software engineer at Harness. I have been a core contributor to LitmusChaos project for over a year and I have been promoting chaos engineering for the betterment of the internet world so that we have more resilient systems, lesser failures, and that every one of us enjoys browsing through the internet. Thank you. Let's create some chaos.
Before we kick off the session, let's take a look on the agenda. We'll start off by understanding the dependency of digital services in the present day and the challenges posed due to its scale of adoption. Then, we'll understand the cloud-native dilemma and how IT service downtimes impact a company. Then we'll take a look at what's chaos engineering and some of its best practices while introducing LitmusChaos. Then we'll finally understand a few different scenarios concerning app resiliency and security that can be enhanced through chaos engineering. And finally, we'll wrap up with a demo of LitmusChaos in action with 2 HTTP chaos experiments. So let us first start by understanding the roots and origins of chaos engineering. Digital services are more relevant than ever before. There are a multitude of reasons for attributing to this. However, the most significant reason include the rapid adoption of internet services by masses, which is becoming increasingly cheap and accessible, along with the factors such as the COVID-19 pandemic, which forced majority of the businesses to go online. On an average, we have 4.95 billion internet users today who spend about 7 hours per day to consume these digital services. To tackle the overwhelming scale of operations required for hosting these users, mostly every business is choosing cloud computing to be the infrastructural backbone of their digital services. And that's how cloud native term has come to be. The applications that run and scale at a cloud computing scale. Even legacy applications are choosing to be cloud native now. However, can we determine their resiliency now that they have chosen to become cloud native? So consider this. Your applications, now being cloud native, stand atop a plethora of other services that determine its functioning and resiliency. You have your application dependencies, then other cloud native services provisioning the underlying infrastructure, the Kubernetes services itself, and lastly, the platform on top of which your application is deployed. Failure in any one of these services can cause your application to not be able to cope up. This problem is only accentuated as more amount of code is now shipped more frequently at a weekly or even shorter cadence, which is expected to run in a multitude of different environments. This unpredictability in the application behavior is the prime cause for service outages, since there is no way to know that how our application will behave when subjugated to an unanticipated situation. So let's try to analyze the impact of service downtimes on businesses. According to a report by Logic Monitor, companies with frequent service outages and service brownouts, that is degraded SLOs, experience 16 times higher operation costs, need twice as many team members, and take twice as much time to resolve the issues. While these figures by themselves indicate the level of threat that service downtimes and service brownouts pose, they don't cover the big picture. But before that, we should also factor in that 51% of these outages and 53% of the brownouts could have been avoided, as found out as part of that report. Therefore, it's a good opportunity to take a step back and try to understand what are the factors responsible. According to the 2021 Data Protection Survey report by VM, the average downtime for an outage was 79 minutes, with the cost of downtime averaging at $84,650. According to ITIC in 2020, 1 in 4 enterprises indicated that a single hour of downtime can cost their firms anywhere from $1 to $5 million, exclusive of any legal fines, fees, or penalties. But the impact cannot be simply measured in cost per hour. There are many other potential downsides to outages as well. So, according to the respondents of the survey, there are 3 different kinds of core impacts. First is the external impact, including loss of customer confidence and damage to the brand. Internal impacts such as employee morale and diversion of resources. And finally, litigation and regulations, which can have a significant effect on company valuation. However, one can still be preparing from the apparent causes that need attention. No one can fully anticipate an overwhelming downtime. With entire applications and their underlying infrastructures now evolving at the pace of hours and minutes for the much needed competitive edge, how can we ensure that our distributed systems always withstand the chaos of the adverse situations? That is by breaking them on purpose with chaos engineering. Chaos engineering is the way to go for all those enterprises who want to prioritize resiliency and reduce downtimes for their customers. It is about adopting a culture of building resilience against unforeseen challenges with their systems. So how does one make a system resilient against something unanticipated? By understanding the system behavior under turbulent situations, which are representative of real-world failure scenarios. The key to successfully practicing chaos engineering is to fully understand the complexity involved in your system through realistic experiment and hypothesis conditions. As far as the general best practices are, chaos engineering is a culture-oriented approach which finds its place as part of the DevOps practices, and hence developers and SREs should work together for the best efforts. While developers should run chaos experiments from an early stage in the development and slowly scale their tests so that all the different kinds of chaos scenarios are covered, SREs should focus on how to make the chaos engineering practices scalable to run into CI/CD pipelines as well as execute the set tests within the staging and eventually in the production environment. Also, it's paramount to have a robust set of chaos experiments that can cover all the different types of failure scenarios that potentially affect an application. Lastly, you need good observability to assess the impact of the chaos throughout the system, and hence your chaos engineering tool should provide with enough insights that can help you understand the impact of the chaos. So these are only a few of the different requirements that a good chaos engineering practice provides. So how can you implement a great chaos engineering practice within your organization? Well, LitmusChaos can help you do that. Litmus is a toolset to do cloud native chaos engineering. It adopts a Kubernetes-native approach to define the chaos intent in a declarative manner via custom resources. It uses the operator pattern and relies on custom resource definitions to define the experiments. On top of that, LitmusChaos provides a UI called the LitmusChaos Center dashboard, where one can orchestrate and visualize the results and metrics of the conducted chaos testing scenarios. It also features the Litmus API for programmatically injecting and managing the chaos, features for teaming and collaboration, GitOps management, and Chaos Hub as an open source marketplace for the different experiments. It's also worth mentioning that LitmusChaos has seen tremendous growth and adoption in major enterprises dealing in all kinds of technologies, further validating the need for chaos engineering and its versatile applications in all kinds of technical domains. Now let us understand a few different scenarios around cloud native application resiliency and security, which can be assessed through chaos engineering. Service latency is a common scenario in Kubernetes. However, it has a profound impact on the application. It leads to degraded application performance, due to which the application might even crash during heavy traffic. This is because the unavailability of a single service can have a cascading effect on the dependent microservices. There are various reasons for service latency between the microservices, such as Kubernetes scheduler and service affinity. The application pods which frequently talk to each other must be co-located within the same nodes, or the containers should be co-located within the same pod, or even the processes can be co-located within the same program. Resource saturation. To avoid resource saturation, ensure adequate amount of CPU, memory, IO are available to all the applications, and there is a hard limit for each container on how much amount of resource it can consume. Lastly, application errors. To avoid this, adequate observability to detect errors must be there, and there should be enough tracing to debug the errors. To simulate latency between the microservices, LitmusChaos HTTP latency and network latency experiments can be used, which affect the applications on the HTTP application layer and the network layer respectively to cause network latency. Internally, the HTTP latency experiment uses a proxy server to intercept and inject latency into the target HTTP applications. On the other hand, the network latency experiment manipulates the TC rules to inject network latency. The next scenario, we have coarse misconfiguration. Coarse or coarse origin resource sharing is a mechanism that allows restricted resources on a web page to be requested from another domain outside the domain from which the first resource was served. Misconfigured coarse headers can have a severe security implications, such as front-end browser coarse error, which causes the front-end browser to give a coarse error and the browser refuses to load the web page. Origin reflection. In some cases, web server generates access control allow origin header based on the origin they receive in their requests, which means any site can access the resource. So if an attacker intentionally changes the origin header and gets back the said header in response with this website and credentials set to true, then the attacker can use this misconfiguration to get any secret data by hosting a HTML page with simple script on his website. Pre-domain, post-domain, and subdomain wildcards. If a non-existing domain having a prefix or a suffix or a subdomain for the intended origin is accidentally allowed to access the data, then an attacker can register that domain and can steal any data. So these scenarios can be simulated by the HTTP modify header experiment, which uses a proxy server to intercept and alter the HTTP response headers for the target application. Now let's head over to Akash for the remaining scenario.
Thank you, Neelanjan. Now moving ahead with scenario 3, connection closed or connection lost. So when the service is not reachable to process requests, then we can consider that the connection is lost, and this can badly affect the application experience. This can happen due to multiple reasons like network failures or network policy misconfiguration, or even the service is restarting or has basically shut down. Now, network failures can have multiple reasons, and proper monitoring and alert mechanisms can help reduce the turnaround time to notice and fix them. We can validate these monitoring and alert mechanism and polish them by simulating network failures using the LitmusChaos HTTP reset pair experiments, which basically simulates a TCP reset connection reset, or the LitmusChaos network loss experiment, which completely blocks the communication to the service. Moving ahead to scenario 4, which is token hijack or man in the middle attacks. Nowadays we use tokens a lot to authorize, process and validate requests, and henceforth sanitization and validation of these tokens at the backend side are utmost important. Bypassing the token validation involves changing the token parameters to bypass the validation. This can be done by various methods like changing the algorithm method in the JWT. For example, if we're not validating the token algorithm, then an attacker can provide none in the algorithm field in the JWT, and the token will get validated even without a signature. Also, using this, the attacker can modify the permission levels in the token, and without validations at the backend for this, they can get elevated permissions to any of the services that we have. Another way is by spoofing the services, especially third-party APIs. For example, the payment gateway service, and without signature validation present at the backend for payment gateways, the attacker can send manipulated responses harming the application. For example, in the payment gateway, validating the payment by acting as a payment gateway service, because we do not have any kind of validation or signature validation at present. So a good mitigation strategy is to have a signature validation for any authorization or third-party API request. And to simulate this scenario to mitigate these issues, we can use the LitmusChaos HTTP modify header experiment to change the headers, or the LitmusChaos HTTP modify body experiment to change the response body. This way we can change either the header or the body of the responses to see if our backend validations and sanitizations are working properly or not, and are we prone to these kinds of attacks or not. Now moving ahead to the scenario number 5, which is a final scenario, API failures, or we can say API responding with error codes. Again, there can be multiple reasons for this, like application is failing due to invalid request, or there is some technical fault in the application. The API can respond with various error codes depending on the issue, and if the application utilizing these APIs is not handling these failures, it can crash the application. Another issue that can be that there are not proper rollbacks in case of API failures, which can result in data inconsistency. Validating the retry mechanism is also important, as improper retrying mechanisms can overload the service. This happened to an application I developed where it took us an hour to debug and fix, which was in between a major event, and the cause behind was the retry mechanism, which kept retrying infinitely and without any wait duration if the service did not respond with a 200 OK status code. Now to simulate this scenario, we can use the LitmusChaos HTTP status code experiment, which can change the status code of the response to our liking, and we can see whether there are certain checks and validations and our retry mechanism or rollbacks are working properly or not. So these are all the scenarios that we want to discuss today. And now we will be moving ahead to the demo. Now let's get on to the demo part of this talk. So I will be demoing 2 of the 5 scenarios that we just talked about. So one of them would be the latency scenario, and the second one would be the reset pair or the network loss scenario that we just talked about. So before I get into the part of like we start injecting chaos, let's just start to get to know about what the application we're using. So what we're using is a simple e-commerce application called Online Boutique, which you can see out here is just a very basic product catalog, and I can click on any of the products, see their details, select quantity, add them to the cart, right, and then place an order, which will basically give me a tracking ID, order ID, and everything, right. And also I have a recommendation system here, which gives me different recommendations. I also have some advertisements running up here with an ad system. So all of this is here, and I also have currency converter in this. I have a cart system in this as well. So all of this is present here in this application, which we'll be using. This is what a simple e-commerce application processes are like. So this is a very simple microservice service application. So everything inside the application is divided into small microservices. Let's talk about what all microservices are running internally. So here we have the ad service, which is used to show the advertisement that I just showed. Then we have the cart service, which is linked to a Redis database. So this stores all the information of the products that are inside the cart of a user, and then that basically show we can use it to place order and everything. Then we have with us the checkout service, which is the complete process of checking out, where it calls the shipping service, calls the payment service, and then calls the email service and everything and internally, and then creates the whole checkout experience. We have currency service, which is used to convert the currency value which we just saw. Email service, which basically sends an email for order confirmation. Then we have the front end, which is used to load the front end. We have a load generator service, which basically generates some loads on the survey on this application so that it feels like some other user are using it as well, to just create an impression of that. Then we have the payment service, which handles the payments and it charges the card. And then we have product catalog service, which is basically storing all the details of the products that we saw, and then showing us the product details and IDs, and as well as whenever we want to order the details for the product at that time. Recommendation service for the email also like section that we just saw. Redis card, the memory database that we have. Shipping service for showing the shipping calculations and proceeding with the tracking ID and everything. So all of these are the internal service that we have right now with us, and we will be injecting chaos on two of the services. So before that, let me just tell you what experiment will be running on. So one of them is the pod HTTP latency experiment, which will be running on the product catalog service. So this will basically show us what happens if the product catalog is the very major service in this whole e-commerce application, because it goes through the whole complete process, and we need this service to show products, to order products and add them to cart and everything. So we'll see what happens if the latency occurs in this service. And the second one that we'll be checking out would be the pod HTTP reset peer experiment, which will basically close the TCP connection between the two microservices, in implying that a network loss has occurred, or maybe the HTTP server is not responding properly or something like that. So that is one more experiment which we'll be injecting on the payment service to utilize like what happens when the payment service is failing when the user is trying to order something, right? So these are the two scenarios that we'll be taking into this for the demo. Go ahead and just start creating a chaos scenario here. So I'm running Litmus in namespace mode. I'll selecting a self agent, selecting the chaos hub. Let's just name it e-commerce HTTP failure. You can name it anything as per your requirement. Let me just add experiments, both of them. Let me just add the latency one first, and now we'll add the reset peer one. So I have this here. Yes, great. So now both the experiments are added. We'll be running them serially, and let me just edit the latency experiment to inject chaos on the microservice we want to. So I'm running everything in a Litmus namespace, and I'll have the label of the service as app product catalog service. So here it is. I'll just add it. I'm not adding any probes. If you want, you can add any probes you want to health for checking the health of the service or checking any specific endpoint that you are targeting. So for all these things you can add a probe, and this will basically set up the base requirement of your experiment to pass. So that is the hypothesis you start off with, and that is what you need to. So probes can be used for that scenario. So we are not adding anything right now, just keeping it very simple. Total chaos duration set as 60 seconds. Then we have the latency at 2000 milliseconds. So that basically means 2 seconds latency here. Let me just confirm the target port of the service. So we are injecting on product catalog, which is running on 3550 port. So this is the port of the pod that we are injecting into, not just of the service. So I have the service and pod both running at the same port. If you have the pod port for that specific application running in different, then you need to set that port, right? So I hope that is clear. Yeah, so now I'll just change this to containerd because I am running my cluster on a containerd runtime. Yeah, pod 50%, I will just leave it open because since there's only one pod available. If you have multiple pods, you can set the value of the pod effective percentage, so that like if you want to target 50% or 75%, whatever pod number you want to target, right? Let me set the HTTP reset pair experiment as well. Litmus namespace. I'll be pushing this on the payment service. Again, not adding any probe. Total cost duration is 60 seconds. Let me just confirm the target service port. Payment service is running on 50051. So let me just put that here 50051. Again, container D as our runtime. Great. So the reset timeout is basically the time which after which the TCP connection is closed. So I'll just keep it 0. You can keep it at 100 milliseconds or to 1000 milliseconds according to your need. For simplicity, I'll just keep it 0 right now. So it will just basically close the connection as to whenever it receives. So there would be like a basic complete network loss happening. I'll keep this reverse schedule off because if we want to see the logs at the later stages or something. So yeah, schedule now, everything else is pretty much similar. Finish, and yeah, so now we have the experiment starting up. Initially it will just basically install the chaos experiment charts and then it will start injecting the chaos. So this in overall would not take up a lot of time. We already have the install chaos experiment running. We shall have the experiment injection phase starting very soon now. Yeah, so great. So now we have the HTTP latency experiment as we just scheduled. It will be starting off first. Just keep a check at the pods here to verify that we have the helper pod up and running. So we don't have to actually verify this from the cluster. We can just see it from here. So it has started already. I can see it from the logs as well. I'll just go here and I'll see what happens. So yeah, so the website we just saw, it was working properly. It had no latency, no lag. Now when I clicked on one of the product to see it, it has started lagging, right? So the response time is getting very slow. Even though I added 2 seconds, I guess it took more than 2 seconds for this to respond. This is also because the load generator is sending multiple requests to this service. So a lot of requests might be getting pulled up and every request are getting some latency added to them. So that is why like every request is getting slower and slower. So I am able to place let's say I'm able to add to a cart. Let's see if I'm able to place the order as well with the latency added. Yes, taking up a lot of time to load. This is surely greater than 2 seconds because of some reasons. Yeah, so we were able to place an order here, and it went fine, but the only thing is like it started lagging a lot, and that is because we added latency. So these kind of scenarios would occur up when we have a lot of load on the service, or when we have so now the helper pod is gone, so the service has started running normally as it was running before. So we can see this. Yeah, so this would happen like when you have a lot of load on the service, or when the server is not responding, when there is a problem with the network connectivity and everything. So these kind of scenarios occur a lot, and we can basically test out like how our service is handling these kind of scenarios if they come up, right? So we can have different health checks where we can see like if the latency is going up over and above our rate, right, and how our services are scaling up, or how our network policies are handling that stuff. So this is one of it. Second, we would have been, yeah, we are into the pod reset peer experiment stage now. So yeah, I just see when the helper pod gets up here, yeah, to save some time. Yeah, it's up. Okay, now let's see. So since we are adding it to the payment service, I don't think we'll be having any issue with any of the other functionalities that is there. Yeah, everything else is pretty much working fine. Let's try to place an order. Okay, yeah, so obviously when the payment service is down, we are not able to place any order, and it is basically giving up the error that it got. So this is also a good thing to like verify what happens if an external payment service that you are using goes down or something like that. So I can see the card is not emptied, so the order is not placed, hence what like the card wasn't empty, so the complete process didn't go through, and there was no issues, I guess, internally. But these kind of scenarios might occur when you have third-party payment services whose services might go down or something like that, and you want to test out like how your platform is performing when their services go out. So for these kind of scenarios, we can run these tests, we can run these experiments to validate these concerns and everything. So after, like right now, we are not able to process anything, we're not able to order anything, but I think, yeah, now the experiment is completed, the helper pod is gone, so we should be able to now place an order. Yeah, so it worked fine after that. So these are two scenarios that would come up in in the normal e-commerce applications, and how we can utilize these experiments to test these scenarios. So let's get ahead and see what other scenarios and how we can schedule them as well. I will not be running them, I will just giving you a heads up on how we can schedule them. So if you just go ahead and add new experiments, we have the suppose the modify header experiment, and what we can do is basically we can go ahead here and inside and tune chaos experiment we can provide the headers that we want to. So what we were talking about, changing the authorization header, so we can just do this and add a randomize value for this. This is not JWT, but any randomized JWT or any modified JWT that we want to add to validate whether like that our application is taking that as a token or whether it's validating or not. Or even in the payment service you can change the headers of the request and responses. So if I change it here to request, then the user from the user to the application whatever sending the JWT, it will be modified. When I change it to response, then if with the second scenario that I talked about, where you want to change the response coming from the payment gateway service, so someone is not mocking that service and someone is not giving a middle attack, so these kind of things can be validated using this. And then we have the status code application as well, which will basically help you change the status code of the application. You can just go out here, and what we talked about, changing it to 404 if a service is not found or something like that, so you can change it. And there's list of status code available in the documentation, which you can utilize here. So yeah, so that is how you can enact those scenarios, use them in your application, and see and check out the resiliency and security of applications by modifying the requests and responses and adding delays or maybe closing the connections. So yeah, that was all from this part of the demo. Thank you. We will be taking up some questions now, and if anyone has any doubt, let's clear them up. Thank you.
Right. So yeah, that was a great demo and session, Neelanjan and Akash. So like we are already running out of time. So if someone have any questions, they can just post it in the Slack channel, and they'll be present there to answer questions. Thanks everyone for joining.
Thank you for having us.
Thank you all.